Hi, I'm Bhuvesh Kumar. I'm a PhD student at Georgia Tech. Today I will be talking about my work on optimal spend rate estimation and pacing for ad campaigns with budgets. This is joint work with Jamie Morgenstern and Oka Shivers. Part of this work was done while I was an intern at Facebook Core Data Science. Before I introduce the concept of spend rate estimation and pacing, let me briefly introduce how online ad auction works. Imagine there's an advertiser who wants to advertise on some platform. So there is some ad slot on which they want to display their ad. So that advertiser will have some value for that ad slot. Based on that value or whatever other information they might have, they will submit a bid uh, to the ad exchange for that ad slot. The ad exchange will set a price for that ad slot. That price could depend on the bids submitted by other advertisers or some bid or some price set by the ad exchange themselves. Then, if the bid submitted by the advertiser is more than the price of the ad slot, then the advertiser wins the slot and they get the value of the ad slot, which is V1, and they spend whatever the slot costed, and their expenditure is P1. But if their bid is less than the price that was quoted by the ad exchange, then the advertiser loses the slot. They don't get any value and they don't spend anything. And this repeats for more ad slots and till the end of their campaign, which could be of length T. But in reality, advertisers don't go and bid on ad slots themselves. In most cases, instead of bidding for ad slots themselves, advertisers run ad campaigns with some budget constraints on an ad exchange like Facebook or Google. For example, let's say there is an advertiser, they might go to an ad exchange like Facebook and Google and tell them, let's say, this is my budget, maybe $100 per day or $1,000 per week, whatever the budget for their campaign is. And then the ad exchange like Facebook or Google, they will bid on behalf of the advertiser on the ad slots, which might be served on Facebook or Google themselves. So uh, Facebook or Google will bid on the behalf of the advertiser, and it's in the best interest of the ad exchange to get as much utility as possible for the advertiser so that the advertiser returns back to them for more business, and the advertiser also wants more utility anyways. To formally define an ad campaign with budget and the permissible strategies. So if an advertiser has a budget B, then it means that over the whole campaign, which is of length T, then any strategy they use, let's use sigma for a strategy. The total expenditure has to be less than B. So here, if you look at this sum is going from 1 to T, which is saying over all impressions. This indicator variable shows that if BT greater than PT, which means that their bid was greater than the price, which means that they won the auction. And if they won the auction, then they paid PT for it. So over the whole period of the campaign, the total expenditure has to be less than the budget B. So for any strategy sigma that ensures that the budget constraint is not violated, so we'll call it a budget feasible strategy. The utility from the strategy is basically the return on the investment made by the advertiser. So mathematically, so if over the whole campaign of length T, the values of the ad slots were V1 to VT and the prices were P1 to PT, then the utility of a strategy sigma is defined, is we use the variable pi sigma for it. So if you look at this expression over here, this indicator variable is indicating if this auction was won, and VT minus PT is the utility if the auction was won. VT is the value for the auction and PT is the price they paid for it. So it's basically the total return on whatever money the advertiser spent. To measure the performance of any budget feasible strategy sigma, we use a benchmark which we call the hindsight strategy H. The strategy H is called hindsight because it has the ability to see in the past and in the future. It can basically see all the realized values, VTs and PTs to decide which auctions to win. So mathematically, it's a solution to this knapsack problem where this Vt minus Pt is the utility for winning the auction. Xt is the indicator over which you're optimizing, such that the total indicator, which is Pt times Xt, is less than B. So here the benchmark is a very powerful tell-all benchmark which can basically do everything, and it's not just a very simple benchmark which can only see information up to so far. And since the benchmark is very powerful, we introduce this notion of epsilon regret. So instead of measuring the regret with the exact utility obtained by the optimal hindsight strategy, we use epsilon regret, which measures the performance with 1 minus epsilon fraction of the hindsight strategy. So as epsilon goes to 0, it means that we are comparing with a bigger fraction of the optimal. So that's our goal, basically, to have epsilon regret for epsilon as close to 0 as possible. So why do we actually need pacing? So the point is that the values and prices of the actual SOR in the future cannot be observed by any strategy. So if you spend too much of the budget initially, then you could land in a situation where there is not enough budget left in the end, and there are high value opportunities in the end, which you end up missing on. And if you save too much money for the future, then you might have leftover budget, or you might end up buying very, you can say, very expensive opportunities with very low values. So you may end up losing on high value items which were earlier in the campaign. So how do ad platforms actually perform pacing? So this is what I'm not saying every ad platform performs this way, but this is a common trend. So they first prepare a spend plan, which is basically how much money they're going to spend as a function of time. This spend plan could be decided by using some proxy, such as how many users are online at what time of the day, or basing some kind of heuristics based on the market availability or some other heuristics. Usually it's some kind of heuristic. And then in second, they use a pacing system to match the realized expenditure with the spend plan. So there's a pacing system. The goal of the pacing system is such that the actual spend is close to the planned spend, which was learned initially. And the spend plan, which is learned initially, which is done using historical data. And since we are talking about ad exchanges like Facebook and Google, they have millions of ad points, actually billions of ad points. So like they have a lot of data and they use a lot of heuristics. So the first idea on creating a spend plan, why not use a linear spend plan? So linear spend plan means that by X fraction of the day or X fraction of the campaign, you should have spent X fraction of the total budget. It's like saying by 50% of their budget, end of the day, 50% of the budget should be spent by 50% of the campaign, and so on. And this has shown to work well if we assume that the distribution of the values and prices of ad slots does not change with time throughout your campaign. So if you assume that the values and price distributions are stationary, then Bolsonaro and Gar in their seminal work, they show that if the values and prices are stationary, then their algorithm achieves an order TRS per half. This is average epsilon regret for epsilon close to 0. Basically, this achieves the lower bound. Bolsonaro and Gar also show that if the values and prices are adversarial, then no algorithm can achieve sublinear epsilon regret for 1 minus epsilon greater than b by t. So basically, assuming that all the values and prices are bounded by 1 here, it shows that there is a barrier of b by t. So no algorithm can achieve more than b by t fraction of the budget of the optimal. So let's say your budget is only 20% of the ability to buy every auction out there, then you might be only competing with 1/5 of the fraction of the what the optimal strategy can get with the same budget. But in reality, things are neither completely adversarial, not completely stochastic. there is some sort of cyclicity in the data and things are somewhere in the middle. So we introduce what we call an uh, episodic model of uh, online ad market. So in the episodic model, you have this T impression, let's say your campaign of length T. We divide it into E episodes, and each episode has an individual distribution for prices and for values and prices. So it's sort of like saying that if you have, let's say, a campaign of a whole day, you've divided the day into smaller chunks of hours, and each episode, let's say, is an hour. So you're saying that within an hour, let's say from 2 to 3, the distribution is somewhat similar, but the distribution from 2 p.m. to 3 p.m. can be drastically different from the distribution that you see from, let's say, 10 p.m. to 11 p.m. But we are also assume some sort of cyclicity in these historical data, which is, let's say, the distribution 2 p.m. to 3 p.m. today is going to be similar to the distribution of 2 p.m. to 3 p.m. yesterday, so that we have some sort of historical data from of the distribution that we were going to see today. We may not have the exact distribution, but maybe based on yesterday's data, we have some historical samples that we can use. Yeah. So what is the solution pipeline that we're proposing for this? It's going to be very similar to the solution pipeline that is currently used in the industry, because we want it to be modular like how it is in the industry, and we want to emphasize that a modular solution also gives the ability to switch apart one part of the pipeline and make it better if you have a better solution for one part. So similar to that, we prepare a spend plan. By preparing a spend plan, we mean we divide the total budget optimally into a budget for each episode. And to do that, we use historical data where we use the cyclicity assumption that 2 p.m. to 3 p.m. today is similar to 2 p.m. to 3 p.m. yesterday. And once we have a spend plan, then we use a pacing system inside each episode with a fixed budget for each episode, for that episode, with that allocated budget. And we show that if the budget allocation is optimal, then the pacing algorithm works optimally to basically achieve sublinear regression. To talk about how we do the budget allocation, we first need to define what we mean by optimal spend rates. So using duality, it has been shown that there is a fixed spacing strategy. By fixed spacing strategy, I mean that there's a strategy which obtains this bid by multiplying each value by a fixed fraction, which is 1 upon 1 plus mu star, obtains the optimal utility in expectation. And this strategy also spends all the budget in expectation. And the mu star here is the optimizer of the dual of the knapsack problem. So if we define G mu as the spend function, so here Vt greater than 1 plus mu star Pt shows that the bid, which is Vt upon 1 plus mu star, is greater than Pt, which means that you won the auction, times the price. So it shows that for mu star, the total spend in expectation is equal to the budget. And this is obtained from duality. And as a consequence of this, we define the optimal spend rate rho E as the expected expenditure of the optimal fixed spacing strategy, basically this strategy, in a fixed round in an episode E. So basically rho E, which we define as the optimal spend rate, is the expected spend in a round E by the fixed pacing strategy. And we use rho 1 to rho E as our optimal spend rates. To approximate the optimal spend rates in our episodic framework, we can show that the total spend, G mu, can be written as a very simple arithmetic expression of the episodic spend functions, which helps us in calculating the optimal spend. So if we can approximate the spend functions, we can also approximate the optimal spend rates. So for any mu, look at the spend function. This first term, which I have represented here, this term is just can be written as a function of the CDF of the value distribution. And a CDF of a distribution can be easily approximated using Hugding style inequalities, and DKW style inequality actually gives us a right bound. But to approximate the spend function at every point, we need to approximate the probability density function of the price distribution as well, for which we use a kernel density estimate. And you can look at the paper for the exact terms or the exact results for each of the parts. So once we have approximate spend functions, we can show that in using our methods, if we have n historical samples from each distribution, then with probability at least 1 minus 1 by n, for all episodes E, if we estimate the spend rates as rho E hat, then we have an additive guarantee between rho E and rho E hat for each E, such that it's between E times order 1 over n is per 1 by 3, and we can see that as n goes to infinity, this gap goes to 0. So once we have the approximate spend rates, we can divide the budget into episodes, and now we have approximate uh, approximately divide the budget, and we can show that even if we have approximate spend rates, we can adapt the gradient descent style algorithm of Balsaro and Kerr, which basically does gradient style updates in the dual space. And we can show that if our approximated spend rates rho E hats satisfy this multiplicative guarantee such that rho E hat is greater than at least 1 minus omega of rho E, then we can get epsilon regret with epsilon equals to omega, such that the epsilon regret is tilde O square root ET. And we can see that this is sublinear in T, as if we divide this by T, and as T goes to infinity, the average regret goes to 0. And you can see that how close we can get to the optimal depends on how well we approximate our rho E hat. And from the previous result, we know that that depends on how many samples we have. So if we combine both the results of the spend rate estimation and the pacing using these approximated spend rates, we can show that the complete pipeline shown in our work can achieve epsilon regret of order square root tilde O square root et using only tilde O 1 upon epsilon cube historical samples from each distribution. We also show some better results for some simpler cases where we make some more additional assumption, and we can show epsilon regret using only 1 over epsilon square samples as well in by making some assumptions on the price distribution. If you look at the experimental evidence, here we have tested 3 algorithms. The truthful spend, which is not shading at all, just bidding whatever the value is. Picked spend, which is the linear, assuming a linear spend rate, or the adaptive pacing strategy by Bolsonaro. And changing spend is the pipeline introduced in this work. And we have tested them on 6 toy data sets, which are designed to mimic real life values and prices. On the x-axis, we have the budget by all budget, which shows that what fraction of the by all budget we have, where by all budget, I mean that if you had that much budget, you could just buy everything. So a fraction of 1 or greater means that you can just buy everything. So truthful bidding obtains the maximum utility. On the y-axis, we have utility divided by optimal utility, which means what fraction of the optimal utility is this algorithm able to achieve. So we can see that for budget greater than 1, of truthful bidding achieves the best utility which is expected, but changing spend rate, which is our algorithm, still achieves much better than Bolsaro and Gar. And this difference is much larger for lower budgets, where it matters way more how the budget has been allocated across episodes. And we can see that changing spend rate does way better than truthful or fixed spend uh, in all cases. And yeah, that's all. Thank you so much.